So here we have the Lagrange variables. We must do the same procedure as we do here to find rho, but it doesn't really matter because we still have the point where things become infinite. And we found, all this stuff is quite simple, although interesting. For instance, to make it more interesting, you see, here we conclude that there is a, generally speaking, at some moment of t, there is a point at which density becomes infinite. In multidimensional case, in three-dimensional case, we will have instead of this relation, we will have the relation and generically this, while here we talked about the point, it's not surprising that the condition that determinant is equal to 0, which is the condition for singularity, is a two-dimensional surface if we are in 3D space, because it's one condition on which you impose, and that corresponds to the objects of codimension 1. Codimension is the difference between the dimension of space and dimension of the object. Why I'm mentioning it, I mention it only in passing, but it's an interesting thing. Those you expect two-dimensional caustics, two-dimensional singularities to occur in generically moving gas of the fluid. And there are theories which actually connect these singularities with galaxies. Galaxies are also flat, tend to be two-dimensional, flat, and this is called the theory of pancakes. Although pancakes in the United States are not exactly the pancakes which the author of this, the Russian author Zeldovich, had in mind. Russian pancakes are kind of crepes, not they're thin, much thinner. But with this important comment, let's proceed. The very important thing, actually, was the statement that at this point, which we made last time, that at this point we cannot use inviscid equations anymore. In fact, the point which we have made was that we look at the equation dt plus vvx. We added tiny viscosity, and we want tangent to 0. And we found a surprising thing, that in fact, while if you are at the moment of time before the singularity, before the end of the world, then nothing happens. You have a smooth limit nu to 0. So what do I mean by that? That suppose this is a solution at some moment of time. It's getting steeper, but not yet very steep. So we have some profile like that. It solves this equation. It also somewhat similar profile solves this equation without this term. The difference between the two, of course it will be slightly different, but the difference between the two solutions will peacefully tend to 0 when nu goes to 0. Because for a simple reason that v is limited and we tend nu to 0, so nothing happens. Not so when we get infinite slope here. In this case, we found we just solved the equation. We found the solution and the explanation for this solution. So the solution was something like, if we send nu to 0, it tends to the, it's called sometimes, it has many names. It's a shock wave. It's sometimes called a kink step, whatever. Maybe there are more names. In any case, we see that near this point, it's legitimate to drop this term. It's important because this second derivative becomes large and compensate the smallness of this term. I will give you a very trivial mathematical example of what happens. We will analyze it slightly deeper in a moment, but let's talk about something completely trivial. Suppose you have not related to the shock waves, but just mathematical example. So math example of the phenomenon, then the order of limits is important. Sorry. So what I'm going to do is to look at the equation. Let's suppose we have the parameter. Oh, let's not to mix it. Let's call it epsilon dy dx is equal to y minus 1. Consider this completely trivial differential equation. And let's not solve this equation, but analyze it. First of all, we understand that at the moment, at x equals 0, it's an arbitrary constant, right? You can find the solution which has any initial value you like. So it should contain an arbitrary constant. And then develop into some solution. But now let's suppose that epsilon goes to 0. If we simply set epsilon to 0, what we get? So it seems that we have only one solution, y equals 1, right? So how this one thing is related to another? What happens really with the solution? What do you think? What can happen? Suppose we can even set y of 0 to be 0, for example, and then we start tending epsilon to 0. So what will happen without solving the equation? What could happen? You see, I'm preventing you from solving the equation because this equation is completely trivial. And you will see in a second what happens. However, you have to do the same analysis with insoluble equations. So it's better to do things quantitatively. Exact solution sometimes is not as valuable as a qualitative argument about the solution.
So epsilon dy dx has to approach a constant.
Yes. So, and good. And so what happens to y?
Then
You start from 0 and then what?
And then so dy dx has to be large such that epsilon dy dx is negative.
Mm-hmm. So basically what happens is that the solution very quickly in the interval 1 over epsilon jumps to 1 and then stays near 1. So it shows that it's very, well, then you can, after that you are allowed to solve the equation and see how it happens. It's very dangerous to set to 0 the parameter which stands in front of higher derivatives, because it can qualitatively change the solution. One last comment about this thing is that how can we see that the true solution is the tanh, which approaches to the step, and how? So we have a certain domain. We have a certain domain in X in which the viscosity matters. Outside this domain, it does not. So let's have a qualitative estimate of the width of the. We want to know what is the interval delta x in which this viscous term is important, and which is in which tanh actually changes from -1 to +1 and so on. So how would you, looking at this equation, how would you estimate the characteristic interval delta x in which you change from say from plus to minus, in the domain in which in other words, I'm asking you to evaluate the width of the shock wave. Shock wave is not infinitely thin, of course. It becomes infinitely thin in the limit nu to 0, but it has certain width, certain physical width. Suggest some procedure, some estimate. It's not complicated at all. What should I do? I want to evaluate all these terms and see their relative magnitude. So if I have Vxx, I have some characteristic velocity v, which is velocity at infinity, for example. Vxx, what's the natural estimate for Vxx? If you know that the velocity changes inside the interval delta x. If it would be a first derivative, what would be your estimate? If you have some function of which you know that it changes by the order of 1 on the interval of delta x. So what is the value of its derivative?
So yeah, so v over delta x is 30.
Yes. So what I'm driving at is that is something quite simple. That it's just v divided by delta x squared. Okay, now I have to compare it with something. So the right-hand side of the equation is nu, v divided by delta x squared. And viscosity is important if it is of the order of what? What I should compare with?
v squared over delta x?
Yes, yes, yes. V squared over delta x. And from this, we obtain that delta x is of the order of nu divided by v. That's exactly what we found in the exact solution, that the width of the tank is just that the width of the shock wave. And of course, I will not be doing this, but of course, when you know that the shock wave developed, you can find the amount of heat it produces and so on. It dissipates energy. What's quite remarkable about the shock wave is that although it exists in the limit nu to 0, let me start again. It's not surprising that if you have finite viscosity, you dissipate energy. Basically, in the Euler equation, energy is conserved, but when you add viscosity, part of energy, because of friction, will go to thermal energy. It will simply warm up the fluid because of friction. What is surprising that when nu goes to 0, you can easily evaluate in the same way amount of energy which you dissipate, and it stays non-zero even when viscosity is 0. And the thing which I told you last time about detonation, when the shock wave ignites the explosive mixture, is just because it's just this energy. Just because the shock wave has energy, it is very hot, the fluid is very hot, or gas is very hot at the position of the shock wave. Now, well, there are many other instances when the shock wave arises. Most importantly, it's well, I probably will not be talking now about it, but just will mention that when you have if you have an object which moves supersonically, then it simply must, suppose you have something which moves with velocity greater than the speed of light, speed of sound, then you can imagine it in the frame where the flow goes this way and this is at rest. The reason why shock wave arises is that the flow here can have no knowledge of the object in front. Why not? You cannot send any signals from this object. Any signal will be dragged back by this. You send signals with the speed of sound, but velocity of the flow is larger than speed of sound. And as a result, this oncoming object is not, the body cannot influence it at all. On the other hand, we have on the surface of the body, we have boundary conditions and so on, which must be satisfied. And the resolution is this. You form a shock wave, and behind it you have subsonic flow, and all conditions are satisfied. And here there is no knowledge except that you just form the singularity, the shock waves here. And that's, of course, very important for airplanes. Actually, supersonic airplanes, they have, I actually saw one and even sit inside one. all these small fighter planes, they have a long pole in front, and the purpose of it is to have a smaller shock wave, and the smaller shock wave means less energy dissipated. Well, we will return to the problems of flight and supersonic motion later. Now we have unfinished business so far. We got the shock wave which is not propagating because we dropped the pressure. And as I said, you can solve the equation even with pressure. So let's do this. Although we will not get anything more qualitatively, we basically will see that the pressure makes the shock wave to move with the speed of sound, but that's about it. All these considerations which we discussed remain the same. So but it's kind of interesting example. So we'll spend some time for discussing it. So we will be talking about nonlinear sound. Let me write down the equations of motion. We have rho t plus rho x v plus rho vx is equal to 0, and we have rho vt plus vvx is equal to c square of rho x. And this is the system of two partial differential equations. As I told you already, when you have partial differential equation with one unknown function, there is this type of equations, the quasi-linear equations, can be solved in general. They can be their solution can be reduced to solving ordinary differential equation, and that we basically discuss. Well, I will explain more of it later. But there are no general way of solving such system of equations. Nevertheless, in the 19th century, Riemann found a wide class of solutions of this thing, corresponding, roughly speaking, there are waves moving to the left and there are waves moving to the right, and Riemann managed to find the solution, general solution describing the wave moving in one direction, say to the left. Well, his method, again, it was just a curious way to work the equation, but generally the method is very simple. The only requirement is for you to find such general solutions is that you have to be a genius like Riemann. And if you are, and then it's very simple. Otherwise, it's surprising. Namely, he said, let's look in the linear approximation. We have rho as some function of x minus ct plus another functions of x plus ct, and analogously v. He noticed that if you consider only the wave moving in particular in one direction, then v will be another function. And so you can try to look for the solution where rho depends on v only. No one guarantees that this solution will exist on nonlinear. It's just some extrapolation of what we know in the linear approximation. And there is no guarantee that it will work beyond the linear approximation, but it does. So let's assume that rho is a function of v. It depends on x and t, but only through this v dependence. And compare two equations. Rho t will be the derivative multiplied by vt, analogously with rho x. So we will get rho prime of v from the first equation, vt plus vvx plus rho vx is equal to 0. So I'm simply using chain differentiation for these terms. And this is the continuity equation. And then there's this equation. We will write down vt plus vvx is equal to c square of rho divided by rho, rho prime of v, vx. We see that actually we can now, let's modify the first, rewrite the first equation once again. We divide it by rho prime, so we get vt plus vvx, which is an important combination, actually, as we learned before, plus let's see, rho divided by rho prime vx is equal to 0. And that's the continuity equation. And we have the second equation plus c square divided by rho prime of v, vx. And now, actually, when you encounter you see, you make some hypothesis about the solution of this equation. And then it's, which is far from obvious that it will work. We plug it in. The first indication, I can tell you, the first indication that that we're on the right track is that we're getting the same objects, the same combination of velocities here and there. And indeed, for both equations to be satisfied, we need just to say that c square of rho divided by rho should be equal to rho divided by rho d rho dv. And we actually get an ordinary differential equation, rho square divided by c square of rho. Again, to solve this, this is very simple. We just set v c square of rho divided by rho square d rho. This is the general solution, and that determines for us the function rho v, which we are discussing. Now all which is left to do is simply to plug it we know now the function rho, and we have this simple equation which we can solve. Namely, we have the equation, the type of the equation which we get is Vt plus Vvx plus some function. Look at this function. We actually can add it. Well, I will not. Let's call it some concrete function f, which we obtained from rho divided by rho prime, which depends on the velocity. You will see in a moment that, in fact, this is the speed of light as a function of the speed of sound as a function of the. Okay, how to solve this? Now you remember our tricks which we did before. What can we? This is the equation which can be solved in most generally. The real miracle already happened. It was the consistency of the ansatz of this substitute with the equation. The fact that the same combination appear here and here, and we can make these two equations to repeat themselves. One should tell us the same as before, and the most important formula is the formula for rho as a function of v. Now we got the equation of this type. How to solve it? We practically solved similar equations.
Wait, sorry, I have a quick question. So why isn't that a rho prime squared?
Where?
Sorry, so instead of d rho dv squared, why is it?
Oh yeah, well, you mean, here? Mm-hmm. Yes, I think you are right, I forgot. Yes, I forgot the square. Yeah, so thank you for following this. And correspondingly, we have d rho dv. It now is plus or minus rho divided by c of rho. So this, thanks. Now, okay, we have it now, but it's now correct. By the way, how would you, already at this stage, how would you explain the plus and minus? Why we should have expected that we have two possibilities? Remember our motivation. Why we expect two types of... Yeah, go ahead, please.
Because the original idea is that you have two waves that travel in opposite directions.
Yes, exactly. We can apply it either to the wave moving to the right or to the left. So we do expect some some two options for the solutions, and we get it. Thanks to you, because I forgot to put the square here. Okay, but all this is nice, but we still have to solve this equation. Let me call it C of B. You will see it's just the speed of sound expressed. So let me write it down again. all reduced now to this one. What to do? What did we do? Remember, without this term, which was there. We solved it very simply. Now with this term. Remember how we solved this equation? What was the idea? Remember the trick we divided by. We first write it down as. That's the first step. And then we did what? Yes. So we got dx dt at constant v. So we find a general solution, which is x is an arbitrary function of v plus c of v t. And the only thing we changed is we added this speed of sound. How now, before we leave this subject, we have to understand this better. Reproduce the linear approximation. What is the linear approximation? When we discussed propagation of sound linearly, and we said there are certain conditions under which you can use linear approximation. And I want you to use these conditions here and to explain to me how linear sound is an approximate solution of this equation. First of all, yeah.
So V much smaller than C.
Yes. Then what you do?
And you just have x equals f of V plus C2.
Exactly. And when we solve it, the simplicity equation, we get just the wave propagating to the right. So in this sense, it's all fine. And we see that if you will start the same analysis with smooth initial conditions, you will obtain the same result, except that the whole kink, will be moving with the speed of sound. And that explains why detonation is such a terrible thing. The explosion propagates with the speed of sound. So, okay. So we had the shock waves. As I said, is just one of the big family of various creatures which exist in hydrodynamics, and it's typically it's a codimension one object, but there are also other objects in hydrodynamics which are generated. So this, when I say object, it's just we start with some flow and we discover that in this flow, for example, you start with the airplane and when it moves supersonically, you discover the shock waves appeared. Actually, it's a purely kinematical phenomenon that this shock wave should appear. You have it in several parts of physics. For instance, if you go downstairs here, probably, then you will find there is this exhibition of old experimental devices. And one of them uses this superluminal motion. What is this? Which is very similar to the airplane crossing the sound barrier. You certainly passed by. If they did, I hope they did remove this. These devices there. I have, but they have been there for a long time. Anyway, what I'm talking about. When else you have what? First of all, what happens when a particle moves superluminally? First of all, it must be in some medium, because in the vacuum the maximal speed is always speed of light. Now, if you have the particle moving with arbitrary velocity in the vacuum, it cannot emit photons if it moves with constant velocity. It's simply a consequence of energy momentum conservation. If you have a particle moving in the vacuum, nothing interesting happens. Energy momentum conservation prevents this particle from radiating. It's another matter if it accelerates, then you have radiation. All that changes when you go from the vacuum to some medium. In this case, the speed of light in the medium can become smaller than the velocity of the particle. And when the particle moves with a with the speed, it actually radiates photons. Energy momentum conservation allows you to radiate photons. That's called Cherenkov radiation, and it's used for checking the speed. It was used before this for the checking the speed of particle which came from accelerator or from cosmos and so on. And the dynamics of it and kinematics of it is precisely the same as that of the shock waves we discussed. Okay, we don't have much time. We probably will return to supersonic motion a little later when we will be discussing flight. There are many other instances of the same phenomenon and so on. I shall not be. Well, our goal now will be to examine a slightly different phenomenon. Namely, we know that when we have two dimensions, the phenomenon which is not present in one-dimensional flow, when you have two-dimensional flow, there's a new object which can appear, and it's vorticity. When I'm saying starting from two dimension, I mean that the shock waves they exist in one dimension. If you go to two dimensions, then the shock, which was just a point, the kink was just a point in X, it will now be a surface, as I said. Similarly, if you have vortices, they are point-like in two dimensions, they are string-like in three dimensions, and they are surface in four, and so on. So we will be discussing them. And we will be discussing them mostly in the context of the two-dimensional flow. It's their natural, so to say, habitat is two-dimensional flow, like shock waves are one-dimensional. Okay. Let's consider now, let's go back and consider incompressible fluid. As we know very well, let's set density to 1. Density is not changing. That's quite different from the shock waves where the density was a very important variable. Here it is not. And we have the equation. This is the pressure, and the condition for incompressibility is this. It determines, as we discussed several times already, it determines the pressure. What is vorticity? Actually, when you have it's very clear that when you have a moving fluid, some accidental torque, since there is no viscosity, no friction, some accidental torque will immediately create a vortex. But what is a vortex? How to describe it? The vortex can be described if you have the point x, then in the vicinity you want velocity distribution, which is, maybe I shall wind it in a different direction, counterclockwise. The lines of the velocity should behave like that. So very nearby, that means that velocity should be orthogonal to the radius vector, and in any dimension, most generally, you would expect, if you Taylor expand the velocity, assuming it's 0 here, this tensor omega alpha beta should be antisymmetric. And from here, you immediately conclude that indeed the velocity is orthogonal to the radius vector. But that's in the vicinity of this point. More generally, you can rewrite it in the following way. You can introduce a quantity located at the point x, which is simply d alpha v beta minus d beta v alpha. This is, in vector analysis, this is what is called a curl. In hydrodynamics, it's a vortex. And you see that if you substitute this expression, then the constant omega here will be the local value of this angular frequency. Omega, but here and here are basically the same thing. It's kind of angular frequencies for rotation. The fluid is rotating, and omega is angular frequency. And as I said, this is called vorticity. Again, I think if you think about electromagnetism, then this curl is some vorticity is something similar to magnetic field, and we will see this analogy in much more detail a little later. And the interest of this, we will now derive the equations for this guy. There are quite a few interesting theorems. Moreover, without vorticity, there is no flight. We will derive the formula that the lift force which exists is directly related to vorticity. So it's an important object and quite beautiful. Let's derive the equation for which governs the vorticity. And indeed, to simplify matters, we will be talking about incompressible and inviscid fluid. All other more general things, more general discussion is possible, but it's not very interesting, and we will skip it. Okay, so first of all, let's derive the equation for the vorticity. And for that, we simply differentiate this equation. And we will get, so we will write down it in, I'll change the names of these guys. And I apply d alpha, and then I subtract the opposite. I apply d alpha, I get omega alpha beta dot plus d lambda omega alpha beta. I will then we will have terms coming from here, which the algebra, I will tell you, I will write the answer, and the answer is actually very simple and nice, and you will check the algebra yourself. So when you start differentiating and subtracting, nothing more than that, you will get this term coming from here, and you also get the following terms. I'll tell you how I remember this. I don't remember this, but I know the principle from which which this term follow. And so this is the equation. I shall also write it in arbitrary number of dimensions. I shall return to it momentarily, but let me now write it down in dimension 2. In dimension 2, there is a quite remarkable thing that actually this stanza contains how many components, independent components, in 2 dimensions. Why? In 2 dimensions.
So this has 4 entries, and you can decide 2 diagonal entries. Or no, it's antisymmetric, so it's only 1.
It has only 1. Actually, the omega alpha beta, it's always the matrix like that. It indeed contains 3 components in 3 dimensions. And that's related. The omega is rotation. The intuitive meaning of vorticity is rotation. And we discussed at the beginning of these lectures that we have 3 independent rotations in 3-dimensional space. How many in 4-dimensional space? 6, exactly, which forms the Lorentz group. And in 2 dimensions, we have simply rotation in the plane, only 1 rotation. Okay, so I shall write down, and that this is often convenient to write it down as omega of x multiplied by epsilon alpha beta. epsilon alpha beta is, we encountered this numerical tensor is just 0, 1, minus 1, 0. It's an anti-symmetric tensor, and in d dimensions there exists the tensors of the rank d. In 2 dimensions it's rank 2. All this is simple kinematics of rotation, which we already discussed. If you have more questions, we can talk about it after the class. But we quite a few times already mentioned this. Okay. It's important to have the equation for 2 dimensions, which we will be using very extensively. In 2 dimensions, we have the equations for omega, and we have the equations omega dot plus v lambda d lambda omega is equal to 0. So in 2 dimensions, these guys, it will take, you will do it at home, that when you substitute in 2 dimensions this thing, these 2 terms cancel, and what is left is this. And that's one exercise. The second problem would be to understand why. What does that mean? And for that, I have to, well, we will examine the meaning of this equation. It has very precise physical and geometrical meaning. Okay. There are several important points here. First of all, there is a very simple, almost trivial, but very important theorem, which says that if you have inviscid and incompressible fluid, and at the beginning there was no vorticity there, there is no vorticity for all time. So such fluid with 0 vorticity, it's called, this flow is called irrotational. I want you to look at the blackboard and to prove this fundamental theorem. That vorticity will not appear in the infinite flow, and with all these conditions which I mentioned. Look at the equation for vorticity and think a little. So, any suggestions how to prove this theorem? That suppose that at initial moment vorticity 0. How to prove that it stays 0?
So so if vorticity is 0, then v lambda omega is always 0. So
yes, that's it. Yes. So it's completely trivial. The only thing which I want to stress is if we talk about the velocity, not vorticity, similar theorem will be completely wrong. Why? What's the difference between the equation for the velocity and the equation for the vorticity?
There's an extra pressure term.
Exactly. That's pressure term which cancels, which is basically angular momentum conservation, that this term exists for the velocity, and therefore you cannot, even if you set initial velocity to 0, it will be generated by pressure, generally speaking. While vorticity if it is 0, there are all terms in the equations are 0. So there's this class of flow, the whole class of flow, which is quite important, which is called the rotational. Okay, now let's analyze what this equation means, and then we will understand this equation as well. But this is obviously more complicated. Let's start with the simple, and our interest will be mostly on two-dimensional flows. So let's look once again. We have omega tx plus v lambda t lambda. Let's suppose, of course, omega depends on v, but let's compare this equation with the equation f dot this equation is f is simply v is a given function, and f is some unknown function. And I first of all want to, let's try to understand what this equation, what the meaning of this equation. First of all, in order to specify the solution, what kind of initial data you need? So we have the solution will be some function of n plus 1 variables. It will depend on time and on x1, xn. So what kind of data I need to present to fix the initial value, the solution itself?
Initial v?
Well, let's suppose v are given. We are not now, at the moment, when we talk about this equation, we are not discussing v development. So v is a given quantity. Okay, I'll ask you a simple question. Suppose we have the equation v is a constant, and we have only one dimensional case. Excuse me, 0. What is the solution of this equation? First of all, what we need to fix to fix the solution, and in this case, what is explicitly the solution of this equation? It's very simple here. If v is a constant, I mean. Let's start with a simple question, which is what is the data? What kind of data we need here to specify the solution? And remember how we several times answered this type of questions. How to approach them? That's basically what I'm. So you have to fix some initial data, right? How to see that initial data are just, you can, in principle, if you do things arbitrary, then you can either underfix the initial data or overfix. If you impose too many initial data, there will be no solution. Yeah.
Could you tell expand out?
Yes. So what you want to fix? So maybe I misheard you. You said that you want Taylor expansion. Yes, but so that's right. But so what? So how you apply it? And what's the answer to my question?
So you can fix. You have the first remove f in terms of.
Yes. So what needed to be fixed?
Just the initial f.
Yes, you are right. You are quite right. Let's fix f of 0 and x, and that's an arbitrary. That could be an arbitrary function. Then you can get f dot. You differentiate it twice. Set t to 0, you get f double dot, and so on. So you indeed reproduce the solution nearby with this initial condition. This, by the way, this method is called Cauchy-Kovalevskaya method for initial data. And you can see the portrait of Kovalevskaya on the third floor. Anyway, I also strongly recommend reading her memoirs, which are quite interesting and lively. Anyway, that answers the first part of the question, but now I want try to interpret this. It tells you that when you when time is changed, you can actually shift x in such a way as to compensate for this change. I am intentionally unclear because I want you to figure out yourself the solution of this equation. For example, if v is 0, the solution is simply f is as 0 and x, right? But if v is a constant, then what is the solution of f of x and t? Well, let's call this function f of x. Then we actually have, I claim that the solution will be f, some function f of one argument. Which argument?
X minus vt.
X minus vt, indeed. So let's check it, and then next time we will explain what's going on. And what is quite remarkable is that this method is applicable to the general equation as well. So let's check it. F dot is equal to the minus v f prime of x minus vt. Df dx is f prime of x minus vt, and you see that indeed the equation is satisfied. Okay, and you can interpret it actually as the fact that some initial data are moved with velocity v, and similar interpretation will be valid for the general case, but let's stop here.